Dynamic equilibrium and Le Chatelier's principle are two very important principles when it comes to dealing with reactions which create an equilibrium, and there's a lot of these in chemistry. You should know that when we have a reaction happening, we start off with a high concentration of reactant. As time goes on, the reactant is used up, and we decrease the concentration of the reactant over the course of time until it's all used up and we have none left. You should also be able to work out then that if we have a certain amount of product, a certain concentration of product at the beginning, which is 0 because the reaction hasn't started yet, as time goes on that will gradually increase over time as well until there is a high concentration of product. The maximum concentration of product has been achieved as the reactant runs out. Some reactions, however, don't work like that. Some reactions, like this one here, which you may recognise, work differently. We have nitrogen and hydrogen reacting together to make ammonia. However, if you leave ammonia to its own devices, it will actually break back down into nitrogen gas and hydrogen gas. And what that means is that this reaction can go both ways. It is a reversible reaction, and so we write a reversible reaction with the reversible arrow. So whenever you see a reversible arrow, there's a good chance that you may well find an equilibrium between these two chemicals. So what's an equilibrium? When you have an equilibrium, you have a situation where, as the reactants are being made, the products are forming, same as before. But actually you'll get to a stage where the product starts being used up to reverse the reaction and make the reactant again. So what we find is that instead of all of the product being formed, and instead of all the reactant being used up, we end up with a situation where not all of the reactant is used up, because the product which is made turns back into the reactant. So as quickly as the reactant is being used up, it's being reformed by the product. So we never get to the point where the product reaches the maximum yield that we could have of product. And we never reach the point where the reactant has actually all been used up either. This is because the reaction is reversible. The forwards reaction is equal in rate to the backwards or the reverse reaction. And that's an equilibrium, where we have a mixture of the reactants and products where the forwards and reverse reaction rates are the same. So if we use this as an example, if we have a look at the forwards reaction rate, as we add nitrogen and hydrogen into a reaction vessel, it will start to produce ammonia. There will come a certain point where the ammonia will then start converting back into nitrogen and hydrogen, and we'll end up with a mix of all three things. Now we end up with a certain concentration of the products and a certain concentration of the reactants, and whether we have more of this or whether we have more of this, we say we have a shift in the position of the equilibrium. Now what do I mean by position? If you imagine that we have an equal concentration of product and reactant, let's imagine that is here. If we increase the concentration of the reactant, we say that the equilibrium has shifted to the side where the reactants are. It's shifted to the left. If we increase the concentration of the product, we say that the equilibrium has shifted to the right. Okay? Now, so the position of equilibrium tells us basically the relative concentration of reactant to product. And that brings us on to Le Chatelier's principle. And Le Chatelier's principle is here, when a system in equilibrium is subjected to an external change, the system readjusts itself to minimise the effects of that change. And what that means is that an equilibrium will change depending on its conditions, and it will change to minimise the effect of those conditions. And here's a couple of examples. Let's take this as an example. We have some chromate ions and we have some dichromate ions, and in order to make the dichromate ions we just add a little bit of acid, and this is a reversible reaction, so it forms an equilibrium. This is our system in equilibrium. So what we're going to do is we're going to put on it an external change, and the external change is going to be the increase in concentration of acid. So if we increase the concentration of acid, we now have an equilibrium which has had an external change. We've got more of this, and so it's going to minimise the effects of that change by trying to then reduce the concentration of H plus again. How is it going to do that? We have increased the concentration of H plus. It is going to try and reduce that again, and the only way for it to do that is by reacting the H plus and shifting the equilibrium towards the right hand side. It can also affect the equilibrium by increasing the concentration of something else. So if we decrease, instead of increasing the concentration of H+, we decrease the concentration of the H+, then we have a system in equilibrium which is undergoing an external change. The equilibrium is then going to minimise the effects of this change, and so we are going to shift the equilibrium to the left. But it's not just concentration, it can work with temperature as well. Temperature affects a system in equilibrium like this. This will be affected by temperature. We have a forwards reaction here which has a positive delta H value. And what that means is a positive enthalpy change means that it is endothermic. So the endothermic reaction will shift the equilibrium to the right. An exothermic reaction shifts the equilibrium to the left. So if we increase the temperature, we will find that we have put an external change on the equilibrium, and so the equilibrium will change to minimise the effects. Because we are increasing the temperature, the equilibrium will then try to decrease the temperature, which means that we are going to go with the endothermic reaction as heat energy is taken into the system. And so the equilibrium shifts with the endothermic reaction forwards. Similarly, if I decrease the temperature, then we'll find that the equilibrium has got an external change on it, and so we are going to minimise the effects of that change. The equilibrium is then going to try and increase the temperature, which means that the exothermic reaction will be favoured and the equilibrium will shift left. Finally, if we have two gases in equilibrium, then what we find is that changing the pressure will also affect this system in equilibrium. We will have an increase in pressure, which will be an external change, and therefore the equilibrium will adjust itself to minimise the effect of the increased pressure. How is it going to do that? Well, it's going to have to lower the pressure, and to lower the pressure we need to decrease the number of molecules that there are. And so here we have 2 molecules, here we have 1 molecule. We can decrease the pressure by shifting the equilibrium to the right, because the fewer gas molecules there are, the lower the pressure will be. So it's opposing the increasing pressure by shifting right to decrease the pressure. Again, the opposite is true. If we decrease the pressure, then we'll find that our system in equilibrium is undergoing an external change, and so to minimize the effects, the equilibrium is going to adjust itself. We want higher pressure. To get higher pressure, we're going to go from having one molecule in a set volume to two molecules in a set volume, and that will increase the pressure. So we're opposing the decrease in pressure by increasing the pressure by creating more molecules.